algebraic methods, other algebraic methods. So what we do with a proof by contradiction is we assume the opposite, and then we show how that would create a contradiction and how the opposite can't possibly be true. Right? So if you think of this, two types of real numbers, rational and irrational. If I can show that if I assume that root 5 is rational, maybe write this down, I'm going to assume root 5 is rational, but then if I show that that's impossible, it's like, well, therefore, so we assume this, then we show that that causes a contradiction, and is in fact impossible. And I can say, well, therefore, it has to be the other kinds of numbers irrational. It's like, therefore, must be irrational. So that's the basic chain of logic that we're following. And you can read more about that in your book. And they have a worked example on page 216. All right. So this is proof by contradiction. And I'm going to make a little bit of room on the screen because I might need it. All right. So if we assume that it's rational, then we could say that it could be expressed as a fraction. Now the book uses P's and Q's. Mind your P's and Q's. So I'll use those. It's really important that we think about this expression. All right, so P and Q, all right, they have to be integers. So they have to belong to the set of integers. And also, it's easy to miss this little sentence in the book here, in the example. They say P and Q have no common factors, right? So they're integers, like you'd expect in a rational number, right? But also, P and Q have no common factors. What this means is the fraction's already in its simplest term. Right? So those are the conditions that I'm defining before I start the proof. It's like P and Q could not be this. Right? That's what I'm saying. But it could be a half. Right? This fraction's already in its simplest term, the simplest form. Okay. And that's really key to the proof. Okay, so now we do some algebra here. How could we manipulate this? We could square both sides. So 5 equals this all squared. Maybe I'll write it up here. That all squared is the same as P squared divide Q squared, right? Bit of a rearranging, I can see P squared would have to equal 5 times Q squared. Therefore, P squared is some number times by 5. It's a multiple of 5. So P squared is 5 times something, right? Multiple of 5. Okay, now the Q squared, it's just a number, right? We started off by saying it was a whole number or an integer. When you square an integer, you get an integer answer. So this is just an integer, and I'm really more interested in the multiple of 5 part. I could even say it follows that p squared is 5 times some number. Let's call the number m or n or something like that. All right. Oh, the book says k. The book uses k, where k, well, I'll stick to m. I've written it now. Where m belongs to a set of positive integers because we've squared it. So it's some integer. Remember the symbol for integer. And because of the squaring that's happened over here, or up here, it would actually be a positive integer, right? Okay. Maybe up here I should have said we can't have P or Q equal to 0. Another one of our conditions up here, P, Q cannot be 0. Right? All right, now what we want to be able to do is go from this step here, P squared is a multiple of 5. We want to be able to say this, therefore P is a multiple of 5. And you need to stop and think about this. Is this really true? And the answer is yes, it is, but it's like if the square of a number has a factor of 5 in it, does that mean that the number by itself also has that factor? And the answer is yes, but only because it's a prime factor. And I think it's best shown with an example. So if we pick 2 numbers, it's always a bit easier, I think, to think about actual numbers. Maybe 12, and what's 12 squared? 144. I'm going to draw up little factor trees. So factors of 12, maybe 3 and 4, they're factors of 12. I could have done 6 and 2. I've chosen 3 and 4. Now that one's prime. The 4 I could break down as 2 times 2. So I could represent 12 as being 2 times 2 times 3 equals 12. These are the prime factors. Could have said 2 squared times 3 equals 12. Right. What about factors that are in the square, right? Like the p squared? Maybe halving, that's easy. Maybe half and half again. Should we get a bit fancy? What about 36 times 4? So 36 is a factor of 144, and 36 is not a factor of 12. Right, so there are factors in the square number that are not in the number, right? Here's an example right here, 36. I could break that into maybe 18 times 2. The 4, that's a 2 times a 2. We're running out of room here. The 18, that could be 9 times 2. The 9 is 3 times 3. And these would be the prime factors. The ends of these little tree pathways, or whatever you want to call them. So these are factor trees. At least that's what I call them, factor trees. And if you keep working down, you end up with prime factors, prime numbers. You can't reduce this. I could say 3 has factors of 1 times 3, but apart from that, these are prime numbers. So 144 would equal 3 times 3 times 2 times 2 times 2 times 2. That's the same as 3 squared times 2 to the 4. What's also interesting here is that if I took 2 squared and squared it, I get 2 to the 4. If I took 3 to the 1 and squared that, I get 3 squared. Right? But so it's kind of interesting. If I square the prime factors in the number, I will get the square of the number, right? But the key idea here is that these prime factors, the 3's and the 2's, that are in the number, they have to be in the square of the number as well, right? So these are the ends of this tree. No, there's other ways I could have gone through a tree here. I could have said 72 times 2, or I could have gone straight to 12 times 12. But I wanted to show that there are some factors in the square that are not in the original number, but all the prime factors have to be, right? Because these are the irreducible factors of the original number. We can't get underneath them. They have to be in the square as well, right? And because 5 is prime, so it's like note bene, note well, that 5 is prime, right? Any prime factor that's present in the square has to also be in the original number, right? So I could say something like, therefore, P could be expressed as 5 times n, okay? And this is really just a method that we're following through. The method's outlined in the book, like I said earlier. Right? So taking this new definition of P as being 5 times some number, let's put it back into this expression that we set up here. We'll put it in here, right? So we say 5 equaled P squared on Q squared. Right? It'd have to be 5m squared on Q squared, right? So therefore 5 equals 25m squared on Q squared. Okay, so 5 Q squared equals 25m squared. Let's divide both by 5. We can say Q squared equals 5 times some number squared. And remember again, this here is an integer. We're basically in a very identical situation with Q squared as we were with P squared over here, right? This is just some integer. And we've already established that if Q squared is a multiple of some prime number, Q squared is multiple of 5, therefore Q has to be as well. And this is the point where we have our contradiction, right? Because this is impossible. Right? We originally set this up so that P and Q were irreducible. The fraction, the rational number, is already in its simplest form, right? We defined that at the start. We said they had no common factors, but we've got to this point now where we're saying Q has this factor of 5, and P also is a multiple of 5, and that can't be. It'd be like P on Q, ooh, what's happening with my pen, would equal 5 times some number, maybe use more of the alphabet here. What's the letter after N? O. I don't know if that's a good number to use, but what, letter to use. But this is a contradiction, right? So this is out. This is a contradiction. So if we are assuming that the square root of 5 is rational, we end up with problems in our algebra, right? And we can therefore say that no, it cannot be rational, it must be irrational. Right.